relatively late in the game, but we're going to be looking at a liquid cooling system and optimizing that system using a combination of 1D and 3D co-simulation. I will talk a little bit about turbo machinery and rotation in the introduction, but the bulk of the presentation is going to be on a liquid cooling system. Again, my name is Arlie Nutzel. I work with Siemens Digital Industries, and I will be presenting. So why is liquid cooling important? So in aerospace, specifically in space as well, these platforms have an ever-increasing power density, right? Size, weight, and power are always being constrained, and it's very important to get that heat out of that equipment, right? For longevity, for reliability. And as that power increases, we have to dissipate more heat from things like instrument panel, avionics, LRUs, any power electronics. As electrification starts to take over in aerospace, it becomes increasingly important to get that heat away. Furthermore, as we move to composite construction everywhere, that's limiting how heat is dissipated. So liquid cooling is becoming more and more important. So for today's presentation, we're going to go through a basic thermal design from start to finish, and look at how we can use tools effectively to streamline the workflow for that thermal design. We're going to start with system simulation, 1D system simulation for the early design. And as we move forward, we'll start ramping in, bringing in more detail, starting to pull in 3D simulation, and then lastly, combining them. Right? The whole point of 1D simulation is to help you get your answers quickly, right? Before you have CAD, before you have a design, when you have a rough idea of what the system is supposed to be for, but not necessarily how you're going to do it. That's where we start bringing in 1D simulation to the mix. So one of the Siemens 1D simulation solutions is called SimCenter Flowmaster. That's a tool that I've been using for the past 12.5 years now. Flowmaster is a vertical solution for thermofluid systems of any size or complexity. Could be flow channels in a microchannel heat exchanger that you model in Flowmaster. It could be in a different industry, something on the order of a large natural gas pipeline, thousands of miles of pipe, and anywhere in between. It's designed to be used by the engineer to create a digital twin of a thermofluid system, help you make informed decisions about how it works, what components to select, what pump to choose, what valve size do you need, and make those decisions early when it's cost effective to do so. You don't want to be changing a pump or redesigning a piping layout at the last minute when packaging concerns have reared their heads. You want to do that early. So just going over some broad capabilities of SimCenter Flowmaster. We are a tool that works in the steady state and the transient time domain. So you can do quick steady state analysis to do pressure, temperature, flow prediction. You can do full on transient for temperature propagation, flow propagation, but also things like fast transient behavior like water hammer and surge cavitation. And then in between, we have a technology, it's really a steady state technology called flow balancing. We'll look at this in a live example in a minute, but what flow balancing allows you to do is back solve for a desired flow rate, size an orifice, size a valve, size a pump, for example, while doing a simple steady state analysis without having to add controls or PID to your model. In terms of heat transfer, we go anywhere from no heat transfer to simplified heat transfer all the way to rigorous heat transfer with conduction, convection, and radiation models. In terms of fluid properties, we can handle incompressible flow, compressible gases, two-phase flow with refrigerants or things like steam water. We can handle rotation in the context of turbo machinery, primarily secondary flow capability. That's flow moving in and out of rotating cavities inside maybe a gas turbine engine or inside a turbo pump. And we also can handle non-Newtonian flow as well. We have a really intuitive and nice to use graphical user interface, so no command lines, nothing like that. Everything's nice and flat and easy to understand. And some nice visual post-processing capability as well. We'll look at that. To make building models easy, we have a preloaded component library. So you don't start from scratch with Flowmaster, you start with a library of components that are pre-populated with performance data, whether that's loss data or pump performance data. You could build out your model, add some geometric data like diameter, length, and you're ready to go. For building models, we find, actually laying out the model tends to be the slowest, most difficult part of using 1D analysis software. So we've tried to solve that problem by allowing you to import models directly from CAD. We handle both piping-specific CAD tools, but also primitive 3D geometry using one of our sister products, SimCenter Flow ESD, which I'll talk about later. Along with that, we leverage 3D CFD to characterize parts. So we have automated technologies to incorporate characterized data from 3D CFD, bring that in and make 1D components out of that characterization study. But we also can do co-simulation with 3D tools. And in particular, with SimCenter Flow ESD, we can do something called OneSim, which is a closely coupled co-simulation where actually all of the analysis happens within one of the solvers. It happens inside the Flow ESD solver. We'll take a look at that as well. In terms of applications for SimCenter Flowmaster in aerospace, the big ones for us tend to be things like avionics, cooling, environmental control systems and life support, propulsion and fuels, really anywhere that liquid or fluid is flowing. For two-phase analysis, things like cryogenics, fire suppression, vapor cycle, environmental control are all relevant. Talked about turbo machinery briefly, but gas turbine secondary flows, blade cooling, turbo pumps, for example. And then for launch systems, things like fueling, water deluge systems, and then lastly, manufacturing, right? Manufacturing is a key aspect, and there's lots of fluid systems there where Flowmaster can lend a hand. So what I'd like to do now is talk about the model we're going to be working with today, how we build that model, and then how we run analyses on that model to do things like rapid what-if scenarios, failure analysis, all in the 1D domain. And that will help us size components, refine our design before it's really set in stone and making changes becomes more costly. So here's the model we're going to look at today. This is very hypothetical. This is not real. It's a large disclaimer. But this is a hypothetical liquid-cooled avionics system for a spacecraft. Could be for an aircraft. Really doesn't matter. So what we have here is a primary loop that directly cools electronics cold plates with PAO, polyalpha olefin. And we pass that heat to a secondary glycol loop with just a plate-type heat exchanger. And that's located here in the somewhat animated GIF. And that secondary system passes flow, circulates it around in a circle with a reservoir, but also passes it through a radiator to dissipate the heat. And so what I'm going to do is I'm going to switch to SimCenter Flowmaster and we can take a look at this model. So I've simplified it a little bit. We're going to be adding some detail to this model, but we'll start simply. So I'll walk you around the model just a little bit. The way Flowmaster generally works is the left-hand side gives me my model-based view or a view into my component library. The center of the screen is the schematic window where we actually do the sketching and the analysis, the pre and the post-processing. And then the right-hand side of the screen is my data entry. So things like length and diameter of lines or orifice or pump data all takes place on the right-hand side. I see that at all times if I just click on a component. So what we want to do in this early model is maybe balance the flow. I know maybe the components on the left are going to be producing more heat than the components on the right. So I want to make sure I have, at worst, an even balance of flow between the two flow paths. And maybe I want to actually impose more flow going to the left and going to the right. I could do that with a valve. I could do that with a flow regulating valve and actively control it. I could size a valve, maybe a needle valve with a proportional controller or a PID controller to find a value. But there's an easier way in Flowmaster, and that's to do what we call a flow balancing analysis. And so what I've done here is I've placed a flow restricting orifice on each flow path, and I've set them with, let me change my units here to something I'm more comfortable with, just an American unit here. So 1.2 gallons per minute flowing to the right, and 1.6 gallons per minute flowing to the left. And what I want to do is solve for diameter. And so what I do is I leave that value blank. And Flowmaster knows to solve for the unknown that I leave it. I could leave empty, let's say, loss coefficient in the context of just a lumped loss. I could leave diameter not set in the context of something like a pipe, opening in something like a valve, pump rotational speed in the context of a pump, but here we have an orifice, so we're going to drive the orifice diameter. I'm going to set this up for a flow balancing analysis, run my simulation, and it's going to quickly iterate. Takes about a second to run, and I can look at results of that simulation. So I'll click on a component, and what Flowmaster has solved for is something we call the selected diameter. So I'll just draw that on the screen so we can see it for both the components. And just to verify we're getting the flow rate we want, if I click on this one, we see 1.2 gallons per minute. If I click over here, 1.6 gallons per minute, exactly what we asked for. And the size that Flowmaster calculated for that particular flow rate, in this case 0.117 inches, and in this case 0.146. Now if we wanted to make them exactly the same, I could just come in and say I want 1.5 and come over to this one, set it to 1.5, rerun our analysis, and it's done. And we can look at the results, 1.5, 1.5, and we can redraw our diameters, and I'm expecting they're going to be pretty similar. Yeah, they're identical in this case. They might differ a little bit, a few decimal places down. No, in this case, they're exactly the same. So that's flow balancing analysis, and it's incredibly useful for solving flow distribution problems. If you have, let's say, a cabin air distribution system, and you want to make sure that airflow is the same from very close to your pack all the way far away, you can do that with flow balancing. So let's switch gears here and start building out this model. We're going to switch to the main model here, and we've swapped out these dummy losses with cold plate models. Let's take a look at this cold plate model and see exactly what's going on here. So in this cold plate model, we have what we call in Flowmaster land a solids network, but it's really just a thermal only network, a 1D thermal network. And that connects to a fluid network with this component here. This component is called a thermal bridge, and it's a convection component. Uses a forced convection model to transfer heat from our thermal model to our fluid model. And we have a couple different choices of how we do that. We can impose just a simple heat transfer coefficient, or we can use forced convection correlation like the Dittus-Boelter relation, which is what we're doing here, to impose a forced convection correlation. Other than that, we have pressure loss and surface area, where we can define that heat transfer rate. Now, into this thermal bridge, we have a heat flow coming from our electronics. So this is the heat dissipation of our electronics here. This looks like a P, but it's actually just spun backwards. It's a Q. And that heat flow source is passing heat into this network. We have a thermal mass that's serving as our capacitance. And then, of course, not all the heat goes into the fluid. Some of it might just radiate or convect out into the equipment bay or into the cabin. So we have radiation and convection that allows us to pass that heat out. So we have a convection component and a radiation component passing heat just to the ambient temperature in that equipment bay. And so we've duplicated that component throughout the model. So we have one for the left-hand side, the right-hand side, excuse me, some power electronics, some communications equipment, another piece of equipment here that's just dissipating heat without a solids model, and then into the secondary loop here. If we want to look at the pump component, we can see we've loaded the pump component with actually the default performance data. So this comes with Flowmaster. We don't have to enter in a pump curve for our pump. It's a generic pump curve, but we've set that with things like rated power, rated flow, and rated head to automatically scale this pump curve data to whatever you have. Should you want to replace this pump curve data with actual data for the pump you're using, that's a simple process. Likewise, if we wanted to apply, let's say, pressure loss and flow rate data, we can also do that quite easily. Pressure loss versus flow rate, or loss coefficient versus Reynolds number. We could set a custom set of performance data here, just like that. We could choose one for let's say, a filter, and it would get applied. That looks something like that. Right? Without that, we'll just use a simple loss coefficient calculation. Now, what I want to do with this model is, right now, we're dumping heat in, and it's going to be stored in this reservoir while this heats up over time. What we want is to add a way to dissipate that heat. So I'm going to add a radiator system to this model quickly. And so to do that, we need some pipes. So I'll just grab some cylindrical piping. And we're going to need a radiator, and that's going to be in our solids catalog. So we'll get a radiation component. And lastly, we'll need another thermal bridge to convect the heat away from the fluid. And so what I'm going to do is I'm going to add some piping, and I can just grab the ends of my pipe, put it like that, and maybe make a copy of that, bring it over here. Take our thermal bridge, put it in place, and our radiation component, and spin around, move it down here. Now, when I have my components in place, I just connect the dots. So I'm going to just drag my components together to build out my model, and I'm done. Now, the last thing I have to do is enter in my geometric data. So nothing is set in these pipes, so I'm going to set a length here, maybe 5 feet. And let's go with 1/2 inch diameter. And to calculate pressure drop by default, Flowmaster uses the Colbert-White equation. So part of the Colbert-White equation is also the surface roughness. So we'll just set that to 10,000th of an inch. Now we've set this pipe. But maybe I want to set all of this easily. I don't want to have to go around and manually click every component in my model to set the same data. That's tedious and error prone. So what I'm going to do is actually copy all of this data to any relevant component that I just added. So what I want to do is make sure I'm only looking at this group of components. So put them in this box called the collection. And I'm going to select all the data I'd like to copy. I'm going to copy that to all the components in the collection. So diameter, length, surface roughness will kind of magically go from here now over to here. So I didn't have to type any values in here. It just set it all for me. Now I do have to, because this is a different name, set my hydraulic diameter here, set a contact area. Let's maybe make this a couple square feet. And sure, we'll use Dittus bolter. For my radiation component, I need to set a surface area. So let's just set this to, say, 30 square feet and give it an emissivity. Just use aluminum for our radiator. And once that's set, I can run a steady state analysis. And no flow balancing anymore. I've actually left the restrictors out, but you can see we run and it takes a few iterations, but it succeeds. And we can click around the model and look at, let's say, temperatures in our model everywhere on the screen. Temperatures are nice, but color codes are nicer. So if I want, I can actually just pop up a temperature profile, draw that right on the screen. So you can see that here. This is heating up, hot flow is going in here, gets cooled by the secondary loop and radiates out. So that is our steady state thermal model that we can use for sizing and model creation. Now, once we have a built up model and we're ready to run, what I want to do now is start throwing maybe a transient scenario at this. I'm going to switch to a copy of this model. In Flowmaster, we can easily just right click, copy a model and start making changes on a new instance without destroying any work. Another nice thing is here, I can make as many changes to my model as I want. Remember, on this flow balancing model, I tried unbalanced flow and then I tried balanced flow. Maybe if I want to go back and see what flow rate I wanted, I could just go back in time, collect that result set and look at what I set that flow rate to in the past, right? So 1.5 versus 1.6. I can go back in time at any time. So now what I want to do is go to my transient model and start looking at what if scenarios. What if the power to my power electronics is non-uniform? What if my pump fails? What if I disconnect my radiator? How long does it take to heat soak, right? We can answer all those questions really, really quickly with Flowmaster. So let's start with maybe a non-constant time variant heat dissipation from our electronics. So I can attach what we call a signal generator or a controller to anything where you see a little yellow flag. So I can control heat duties, I can control temperatures, I can control masses, I can control pump speeds, flow rates, valve positions, anything I want with a controller. These controllers can be just simple lookup tables or state charts. They can be curve data, they can be an equation, they can be feedback, right? So if I wanted to incorporate a PID algorithm, I could absolutely do that and regulate, let's say, the speed of the pump or a position of the valve based on temperature. But in this case, what I want to do is just regulate heat flow rate. And I'm going to do that using a curve I've already defined that starts at 1 kilowatt, ramps up to 3 kilowatts for a time, comes back down, ramps up to 2.5 kilowatts, and comes back down. If we wanted to make a new one of these, we easily could. We could just create a new chart, fill out the data table for that data, and it would pull it right in for us. All right, so I'm going to run a transient analysis, and I'm going to run that transient analysis with some real-time results displayed. We'll see some charts automatically appear on the screen for temperatures, but we can also draw those temperatures right on the screen as the model runs, which is very, very nice for spotting maybe a flaw or a problem in your model early before you take too much time. All right, so you can watch this model develop. This is, we're running a very coarse time step, so this model is running extremely quickly. It's running, I don't know how many times real time, but you can see we're already over an hour into the simulation in about 10 seconds or so. So it's very, very fast to do these rapid transient scenarios. Now, from here, after I've run, of course, I can pull up that temperature result, and we can look at that on the screen. We can animate that, and it will play back in real time, not simulation time. So I can ramp that up to speed up the simulation a little bit so it ticks by a little faster. I can also look at different results. I can look at, let's say, mass flow rate. And the nice thing about looking at mass flow rate is, in addition to a color code, we can also size the pipes by the magnitude, but we also draw flow arrows. In 1D models specifically, it can be very confusing to tell where the flow is going. If I click on an individual component, like let's say this T-junction, and I look at results at, oh, let's say time equals 5 seconds, I can see my flow rate is, let's say, a positive value here. So, okay, great. Arm 3, my flow rate is positive. That means it's coming out. But which arm is arm 3? I have to come in here and mouse over to determine what arms are what. With this visual post-processing, I get a nice little flow directional arrow, and I can see exactly what's going where and to what degree. Right? So that's a very, very nice tool to be able to see where flow is going, how much, what direction, etc. You can look at velocity, pressure, pressure drop, loss coefficient. Anything we'd want to interrogate, we can see right on the screen. So that's one scenario. Let's look at another. Let's fail a pump. So we'll come into this pump, and we'll set up its data form to, after, let's say, 1,000 seconds, let's just trip the pump off. And it will use a built-in inertia model to not suddenly stop, but slow down over time. So we'll run this model again. And like before, the model is going to heat up. 500 seconds, we introduce a little bit more power. But at 1,000 seconds, we shut the pump down. And now we're starting to see temperatures climbing, right? As we don't have that ability to dissipate the heat in the radiator system, it's just going to stay there and spike up. When that spikes up, what's happening is we're not going up to infinity because we did leave this backup heat transfer mechanism, right? We're modeling the convection and the radiation out to ambient air as well as the liquid cooling. So it's not necessarily a dire situation, but it is a problem, right? But we want to make sure we design for redundancy and we have another heat transfer mechanism should that pump fail. Maybe we have 2 parallel pumps. We could test that as well. Right? So that's the transient analysis. Now what I'd like to do is focus a little bit on the detail here, right? In our analysis, we used just a forced convection coefficient, which assumes a cylindrical pipe. That might be fine for you know, a simple heat exchanger or a very simplistic cold plate where you just have maybe a serpentine tube moving through a plate. But in all likelihood, you're going to have some heat transfer enhanced surfaces, things like pins or fins, to increase the turbulence, increase the heat transfer in that cold plate. And we're not capturing that here. So what would we do to capture that additional physics? We could come up with just a wild guess for the heat transfer coefficient. We could look it up in a textbook. We could use engineering know-how. We could do a bench analysis, right? So we could go to a lab, take our cold plate, add some instrumentation, run some flow through it, and define our heat transfer behavior. We could go to the vendor and ask them for it. Or we could use 3D CFD to determine that. And that's long been a way to develop data and characterize and create 1D performance data for 1D analysis, is to turn to CFD. But it's always been a bit of a manual process. You need to go to CFD, you need to mesh the model, you need to run an analysis or several, you need to tabulate that data into Excel, maybe reduce it a little bit, and then once you're done with that data, send it over to Flowmaster, build out your table. Not to say that's impossible, it's something that engineers do every day, but it can be time consuming. So what can we do to streamline that process is the next topic we're going to talk about. So let me switch back to the presentation and let's look at using 3D analysis judiciously to add detail and fidelity to a system model, right? We could just throw this whole thing into 3D CFD now, model the whole system, but that would be computationally and time expensive to do that, right? So what we want to do is kind of do the best of both worlds, take detail from 3D CFD and bring it back into 1D CFD. So to do that, we're going to look at a cold plate model. This is an IGBT module, integrated gate bipolar transistor power electronics module that you use for switching high current devices, things like motors or inverters, battery chargers, et cetera. And we're going to model flow through a cold plate, right? And we're going to do that in a tool called SimCenter Flow ESD. So what is SimCenter Flow ESD? SimCenter Flow ESD is a tool that was part of a group of tools that Flowmaster was a part of prior to our acquisition by Siemens a few years ago. And what Flow ESD is a fully CAD-embedded 3D computational fluid dynamics tool. EFD actually stands for Engineering Fluid Dynamics. We've designed this to be a tool that is easy for the engineer to use, understand, get along with, and really we've strived to reduce the amount of expertise required to get good results out of CFD and bake as much automation into the system as possible. So we start by embedding it within popular CAD platforms, NX, which is what we'll look at today, PTC Creo, Dassault CATIA, Siemens Solid Edge, and Dassault SolidWorks are all supported platforms. Again, the user interface we use is very engineer focused, not necessarily CFD focused. So it makes sense to somebody that maybe doesn't have a PhD in computational fluid dynamics. And we bake in some nice to have things like multi-variant, multi-parameter what-if analysis, things like changing temperature, flow, power, even CAD. So because we're CAD embedded, we could maybe change an experiment based on pipe diameter or pin size, which is what we're going to do here, and see how that affects the thermal performance. We also bake in multi-parameter optimization into the software. So maybe we don't want to go through the effort of deciding if we want staggered or inline pins or what size they should be, what diameter they should be, what flow rate we want. We'll just let an optimization tool solve that for us. So we have a very efficient way of doing that. Again, to the point of making this easy to use for typical mechanical or design engineer, we automate meshing and solution. So the meshing is very straightforward. It's point and click. You decide where you want mesh, where you want more mesh, and the mesher takes care of that for you. It can be as manual as you want it to be if you know what you're doing. But if you don't know what you're doing, you can throw the default mesh on geometry and typically get very good results out of the solver. So we did a design study trying different surfaces flat plate, otherwise known as zero enhanced heat transfer surfaces. This is kind of like the setup we had in the Flowmaster model. But we also tried pins, both aligned and staggered, and fins, both aligned and staggered. We did this parametric study over 16 points, so varying flow rate, temperature, and geometry. And if you look here, we can see how this shook up. So setting up the model from pre-existing CAD, defining materials, setting boundary conditions, setting up the mesh, that took about an hour and a half. The solver time for each individual case, or for the initial case, took 2 hours to solve, including the meshing time. And then post-processing the results, maybe making these nice, pretty pictures, took about an hour. So total time to run a single case here was about 4.5 hours, which, we've seen in the field, up to 10 times that amount of time with traditional CFD. Not necessarily in the solving time. Solving time is pretty standard, and is hardware bound. But in terms of preparation and meshing is where Flow ESD can save a very significant amount of time. Excuse me. Now, our parametric study that we ran, once we do the meshing once, we don't need to do it again. So that study can be a little bit more efficient. That entire study took about 9 hours to solve in this particular case. And here are some nice temperature plots for you to look at. And you can see by staggering the pins, obviously we introduce more obstruction to the flow, which tends to even out the thermal behavior, but might introduce some additional pressure drop. And we'll see that in a second. So here is a plot of temperature versus pressure drop. And these data points are sized by mass. So obviously, in a perfect world, what we'd want to do, if we don't care about anything else like energy costs or pump size or mass of a spacecraft, maybe we just go for minimum temperature, right? So this might be the best. Or maybe our goal is mass and nothing but mass, right? So we want to go with the smallest. And maybe we're not so worried about longevity. We just want to make sure we're not going to destroy a computer or an IGBT with one flight, right? So maybe this is the best. But maybe we have a reusable spacecraft and longevity is important, size of the pump is important, energy cost is important, and mass is important. And that leads me to choose this design in the back, which is actually the aligned pin scenario. So that's the smallest, the second smallest mass, but a relatively low temperature and a relatively low pressure drop. So that's the design we'll go with. Here's another view of that data, just maximum component temperature over the entire geometry, not average temperature, but the hot spot, overall pressure drop, and flow rate. Right? So again, we can see our pins aligned case is not the best on every measure, but overall is the best for our use. So once we have that, what we want to do is we want to build what we call a response surface model. And we can do that by manually running a parametric study, exporting the data, model it in an external tool, reduce that data in something like Excel and bring it back into Flowmaster. Again, I mentioned before that's time consuming, could be error prone. We can just let Flow ESD handle all the work. I see a question, how does Flow ESD compare to Start CCM Plus, which is another Siemens tool? I'll bring that up in just a moment. I'll come back to that question. So let's go into Flow ESD and take a look at it and see how we do here. So what we're looking at is Siemens NX, and when you install and run Flow ESD, you get an added menu bar item called Flow Analysis, and you get an added item in the tree here for Flow ESD. And so really this is just a CAD model, right? There's not a lot going on here. But when we take Flow ESD into account, we can start in a very CAD-centric way defining our problem. So I'm going to turn off these results for just a second. Just going to hide these so we go back to just the raw geometry. And what we're looking at here, let me change my view, is the underside of an IGBT. So here are the here's the die. So these are the transistors and the diodes on the IGBT. There's, you know, a solder plane, some potting material. Here's maybe a heat spreader, and then our copper cold plate, or maybe this an aluminum plate with a copper plate inside with some fins and pins. And so what we have to do is we have to take this raw CAD and we have to set it up for a CFD analysis. Now in traditional CFD, what you have to do is you have to take this, you have to make basically a flow negative, export that fluid body to an external tool, and then mesh it, and then run your simulation. The beauty of Flow ESD is it happens all within the CAD. I don't have to pass the model anywhere. I can just take the raw CAD and start working with it. So moving down this list, I've defined a computational domain, which is just the universe that our model is going to operate in. I've defined material types, so aluminum for this outer solid, copper for the plate and the heat spreader, thermal paste, some copper, some ceramic substrate, a solder joint, and then silicon and insulator material at these lids because we don't want to transfer heat via conduction out the fluid openings, right? So that is the heat transfer properties. Then we have our fluid boundary conditions. And again, we just click on faces. Volume flow inlet, pressure outlet, we'll pull that over here, and we can define those. And then in terms of heat flow rate into here, we can define that as a constant, or we can actually define that as a time variant signal. So we can do a transient analysis here as well and vary this heat flow rate over time, right, with a time dependency or an equation. Then lastly, we create what are called goals. Goals are really just convenient measurement points that allow us to look at, let's say, the maximum temperature of this chip, or the average temperature of the fluid leaving the system, or the pressure at our volumetric flow inlet. That's what goals are for. But the beauty of goals in Flow ESD is they actually inform the solver to drive convergence. Therefore, without even really thinking about it, just telling Flow ESD what's important to us in terms of results, we are telling the solver to use those as convergence and solution criteria so that the solution doesn't stop iterating until these values have come to convergence. So very, very handy. Now, we run an analysis from here as well, and we can click run. It'll run a single analysis, and we'll get results like we saw here. So I can draw a nice cut plot of, let's say, contours of temperature with, let's say, flow trajectories or streamlines right on the screen. These are driven by the GPU, so as I zoom in, they just keep redrawing automatically and get finer and finer and finer, which is really nice. Maybe I want flow trajectories. Again, I can color this by velocity or temperature or whatever I want. Here they're colored by temperature. We can zoom in and see that. We can turn off the geometry so we can really get in here and look around. And that's all nice. We can do our post-processing. We can take our goal plot and we can manually look at this data. But what I want to do is characterize this geometry and bring it into Flowmaster. So to do that, I'm going to make a parametric study. And I'm going to open my previously created parametric study here. And here what I want to vary is flow rate over a range and temperature over a range of values. And after I do that, it will build out the scenario for me. I tell it how many runs I want to make, maybe 20, 50, 100. The more I add, obviously the longer it takes, but the more detailed and smooth my resulting response surface model is going to be. But here you can see I ran this the other day, and it did take about 9 hours to run all of these cases. I just ran them overnight the other day. And we can see our volumetric flow rate and temperature inlet. And what we've done is automatically tabulated the results necessary for Flowmaster. That is temperature, dimensionless mass flow, which is really Reynolds number is a way to look at that. And we call it dimensionless mass flow because it has a sign, and you don't really think of Reynolds number as having a sign. And then dimensionless pressure drop, which is actually just loss coefficient. And then we also look at enthalpy and net heat flow, right? And once that runs, what we can do is create a response surface model from that. And if we wanted to view that response surface model, we could view it. in multidimensional format. We only have 3 dimensions here, so we can visualize it in 3 dimensions. If we had more inputs, let's say we had a 3-way T-junction or a manifold with multiple inlets and outlets, this tool absolutely works with that and can make multiple input and output components in Flowmaster. We call those N-armed components. We could visualize based on a single data point for most of the data and then plot remaining 2 on 2 axes. Sorry, I'm not trying to make everybody dizzy here. I'm just a little slippery with the mouse. And so that's our response surface model. Once we're done with that, we can export a file that Flowmaster can understand called a Flow N-arm file. So really quickly, I just want to address the question, how does Flow ESD's features compared to Star CCM? Obviously, they're different. They're targeted at a different audience, right? Star CCM is targeted towards a CFD analyst. It is easy to use, right? It's got some automated meshing tools like Flow ESD does, but it's really catered to more the CFD analyst. Where Flow ESD is simplified, we don't have as many capabilities. We can't do, like, let's say, as much as the advanced physics as Star CCM can, but we can absolutely do heat transfer, compressible, incompressible flow, 2-phase flow, even hypersonic flow, advanced radiation modeling, combustion. We can do all that in Flow ESD. But if you really want advanced physics like thin films, like condensation and evaporation, like let's say particles, that would be a CCM application where Flow ESD is more streamlined, right? Now, from here, we want to take this back into Flowmaster. So I've exported the data. And now what we want to do is combine the tools into a best of both worlds. So what I want to do is come back to Flowmaster, and I'm going to open a copy called Flowmaster Capsule Cooling SBC, right? And I'm actually going to open up a copy, which does not have a component here. I've removed this block. And what I want to do is incorporate the work we did in Flow ESD. So what I'm going to do is I'm going to create a new component using Flow ESD N-arm component. I'm going to import that file that I saved and put that here, sbc export.flow N-arm. It's going to read the data, look at its configuration, how many arms does it have, what is the nature of the data. Once that's done, we can move on to the next step, take a initial look. Oh, I clicked through that too quickly. Let me do that again. Only click once. Now, from here, what I can do is I can get my image where I like it. I can take a screenshot. That's going to become my component symbol. I can look to see that my thermal data, my hydraulic data, my branch data all looks good. Then I'll click Create. And that brings up a component customization form that's showing up on the wrong monitor. So let me pull that over here. And from here, I can define where my inlet and outlets are going to be placed. I can preset some data in there and then save it. So now what I'm going to do is I'm just going to drag that into my model. And here it is. I'm just going to drag it over. It's going to pull it into my model. I can resize this component, make it a little prettier, and I'll hook it up. So there's my outlet, there's my inlet, and now I can go and run the exact same transient analysis I did before, but instead of relying on Dittus-Boelter or an equation-based correlation, I'm really just reading it off a multidimensional lookup table. Actually, I opened the wrong model here. Let's do this one. This is that same model, but we can just run the analysis and it will go ahead and run, and we can see it's pulling from that lookup table. It takes a little bit more time because it's interpolating the data, and I've changed the nature of the simulation, so it's not running anywhere near as fast as it was before, but it is still quite fast. It's running certainly faster than real time, right? So that is what we call SBC, or simulation-based characterization. Now, that's great if you have the time to pre-process the data and your model meets certain goals, like let's say it's a valve, we're not manipulating the opening of that valve, or we don't want to, let's say, change the power going to this component, right? It's really just kind of fixed in the state where we ran it in Flow ESD. Now, those compromises might not be acceptable, and typically the only way around to get around them is to do something like co-simulation. And traditionally with co-simulation, you're taking a tool like Flowmaster and you're linking it to another tool over technology like FMI, which is something that we support, or you know, creating an adapter to let, let's say, Flowmaster talk to another tool. Could be something like MATLAB Simulink or ANSYS Fluent or any other tool out there, right? We can absolutely do that. But what we've done with Flow ESD is connect them in such a way that the simulation is actually happening inside one solver. That's why we call this one sim. And so what we can do from here is go back to our model, and we can export a connection file. So here I'll just export a one sim export file. I'll save it in that same directory. And in the interest of time, I'm not going to go through the process of creating the component, but it's the same as what we did here. We'll make a new Flow ESD one simulation component. All we do is change the symbol, assign it. And so from one sim, we're going to go into the model. We're going to add it to our network here. Looks just like it did in the SBC case because it's using the same image. But when I run the simulation, something different is going to happen. What's going to happen is it's going to look like we're running directly inside Flowmaster. But what we'll see here is another iteration counter for Flow ESD. And what's actually happening is this entire model, the whole matrix solved for the 1D model, is being embedded within the external Flow ESD solver. And everything is being run from within Flow ESD as if Flowmaster were the boundary conditions extending outside the 3D geometry, because that's precisely what we're doing. We're marrying those boundary conditions between the two models and linking them together in a single solve. So now you can obviously see the trade-off. We're not running at faster than real time anymore. It is slower, but it is you know, as precise as the data we would get inside Flow ESD, right? So these two tools are closely coupled. That gives us advantages for stability. It is faster than running a traditional co-simulation because we're not adding an additional layer, trying to synchronize the clocks. Everything's being controlled by the two softwares and happening in that single solver. So it's an extremely, extremely powerful tool. Looks like we have another question about validation studies. So yes, both tools, so Flowmaster and Flow ESD, have validation studies that we publish on our website and built into the help files. Flow ESD specifically has validation studies for our approach with meshing and solution and the way we handle the boundary layer. And you can, we can absolutely distribute those so you can see how they stack up with traditional CFD. Just as a note, one thing I'll say about Flow ESD is that the methodology we use for what we call grid independence is a very 1D analysis type of technology. As the grid, as the mesh gets coarser and coarser and coarser, in traditional CFD, your model results would tend to fall apart, right? If you don't have sufficient grid cells to model the boundary layer or near the wall or near geometry, you're going to get you know, not so nice results, although that's sometimes difficult to tell without comparing to test data. In Flow ESD, what we do is as the grid gets coarser and coarser and coarser, we start to interpolate in what we call engineering methods, right? So we know what flow past a flat plate looks like in terms of the behavior of the boundary layer. We know what flow over a cylinder looks like. And what we do is we basically take those textbook behaviors and bake them into the solver so that when our mesh becomes so bad we can't solve full Navier-Stokes in an accurate way, we pull in what we call these engineering methods. And as a consequence, our solutions look very good and stay very stable even as the mesh quality deteriorates to almost an extreme degree. So we also have validation studies and results on that front as well with grid independent studies. So you can see how our results stay very good as a function of grid density. Hopefully that answers the questions. I'm getting close to end of time, so I'm going to go back to my presentation and conclude, and then we'll open it up to any questions you guys have. So again, you know, what do we get out of this, right? So 1D analysis, those of you that are familiar with it know, helps us make informed decisions early, right? But as we start to need to look at real world behavior, failure analysis, emergency scenarios, redundancies, you know, 1D can help us with that, but only to a point, right? As we start to define our system and add more detail in the real world, we need our model to keep up with that. And Flowmaster is very good about keeping up with that to a point, right? But sometimes access to vendor data or physical test data is impossible or impractical. So that's where we can start bringing in 3D simulation into the fold, tying it into the 1D analysis, plugging the two together, and really integrate that workflow to take advantage of the best of what 1D simulation has to offer, which is speed and ease of use, and what 3D analysis has to offer, which is accuracy and, you know, what you see is what you get. Sometimes it can be quite hard to make a 1D model look like reality, right? Even though you feel like it should be simple, it's more like a PID diagram than a slave to the actual CAD. So adding that fidelity you get with 3D CFD is really critical. And with that, I'll wrap up and open it to any other questions that anybody has. Be happy to sit here and answer them. So how do we import models into Flow ESD? So that's the beauty of Flow ESD. It is right on top of the CAD platform. So step files, part files, as long as you have a CAD assembly, you can build a model. So if I wanted to open, let's say let's see, some CAD of, let's say, an oil filter, right? I can just pull that in and start clicking on faces and defining things like boundary conditions, porous media, to assign my goals. It's very straightforward. If you can do it in CAD, you can do it in Flow ESD. The only thing you might have to do is what we call geometry preparation. Now, Flow ESD needs a watertight, or we call it watertight, but a fluid tight boundary if you're going to do an internal flow problem, which is what we've looked at so far, right? So flow in, flow out through a pipe, it needs to be watertight. And so we have some built-in tools to help you seal geometry. We have what we call a lid tool that makes this solid geometry. So if you know how to view CAD, but you're not necessarily an expert at drawing in 3D, rest assured you don't have to make these shapes, although they are primitive. You can use the built-in lids tool to generate them for you. And then literally you just take the CAD, you click on faces that you want to make boundary conditions, and you're ready to go. So it's very, very CAD-centric. Hopefully that answers that question.
Arlie, this has been a great presentation. Thank you very much.
Yeah, of course, my pleasure.
We're going to hold it open for a few more minutes here in case there's a question, because I think there's there can be a lag here between the stream. And
yeah, absolutely.
Learned a lot from your presentation here.
Excellent.
So we're going to make a last call here. There's an hour break between right now and the next vendor session, I believe. So I think, anyway, thank you very much, Arlie. And I'm going to let Parker jump in here in a second if we don't have any other questions. I don't see anybody else in the chat session. So
okay.
I think we are.
Well, yeah, just want to thank everybody for attending and appreciate your time. And if you have any questions, by all means, you can follow up with us.
Arlie, maybe put up your, do you have your contact information? one of
You
your
know, I
first
didn't
slides?
think to put it in here, but I can edit the slide really quick and do that. So
Yeah, why
that's
don't you
not a
do
problem.
that? That would be excellent. Okay, I see a question just popped up, it looks like.
Sure.
1 second. Okay. When would you use AMESIM over Flowmaster and vice versa? AIMSIM.
Yeah, I think that's a very good question. So Flowmaster is pretty new to the SimCenter portfolio, and for a long time competed with our other SimCenter tool, SimCenter AIMSIM. SimCenter AIMSIM is a broader tool. It has more capability when it comes to mechatronics, so mechanical motion, things like pump design, valve design, hydraulic actuators, things that are moving. Those are all excellent applications for AIMSIM. Now, AIMSIM is a transient tool, which means some of the things you might want to do in a fluid system model, things like just a quick steady state analysis, things like flow balancing like I showed today in that first example, are a little bit more cumbersome to do in a tool like AIMSIM. They're not impossible, you can absolutely do them, but they're a little bit more cumbersome. Flowmaster is very application driven for pure fluid flow, where AIMSIM is a multi-physics tool that does fluids. So hopefully that distinction makes sense. There's a large degree of overlap between the tools, so your best bet is, if you have that question and you're looking at 1D analysis software, by all means come to us. We help you find the right solution. And sometimes that solution is a combination of the two. And so we've been working very hard on the time we've been together now, adding tools to allow AIMSIM and Flowmaster to co-simulate and share data. So that's something we're actively working on.
Okay, I see. So you just said thank you for that. So I think you answered his question, and some other comments that you've given us a very interesting presentation. So thanks, folks. We have about a minute, and since there's no one right behind us, just give you guys another 30 seconds or so here if you've got another question, since there is a delay between the stream and broadcast. All right, and Arlie, you're putting your phone number there as well.
Yeah, if anybody wants to reach out, might as well.
Yeah, excellent. Okay. Well, excellent presentation. Thank you very much. Looks like we're going to conclude our session here, and we appreciate your participation, Arlie. This is very helpful. I'm actually going to forward this to some people in my group back at JPL.
Excellent. Well, thanks for the opportunity, and thanks for your time.
Thank you, Arlie.